Welcome to the fourth video in the evolution unit where we're going to be talking about how different species form. So up to this point, we've kind of talked about the basic mechanisms of natural selection, and now we're going to actually talk about how those mechanisms of natural selection, amongst other things, lead to the formation of new species. So to get started, let's look at a couple of definitions. We already know that evolution is the change in heritable traits in a population over generations. In other words, I go from a population that has one set of traits 1 year to several years later, I have a population with a whole different set of alleles. So a new word that we haven't seen in quite a while since the beginning of the year here is population. And we're going to define population as a group of individuals of the same species living in the same space at the same time. So this is the smallest unit that can evolve. Remember that we said that individuals cannot evolve, only populations can? So an example might be a bunch of the same species of birds living in a tree at the same time. And then just as a reminder, we're also going to define species as a group of populations whose members are capable of interbreeding and producing fertile offspring. So if an organism can mate with a different organism and have fertile offspring, it's considered to be of the same species. And then a couple of new vocab words we're going to say for the first time. The first one here is gene pool. This is just all of the genes in a population in any one time. So if I was talking about the human population of the United States, so my population was the humans of the United States, if I took all the genes that all the people had in the US, we could call that the gene pool. Or I could look at all of the cardinals that live in the tree in my backyard. If I took all the genes from those cardinals, that would be the gene pool of that cardinal population. So up to this point, the evolution we've talked about has been actually what we call microevolution. This is where we see very small changes in the gene pool over a couple of generations. So if I had a bunch of rabbits living together who were white and black, and for some reason the black ones blended in with their environment better, so they survived longer and had more offspring, and then 10 years later I had mostly black rabbits, that would be microevolution, because I'm seeing only a slight change in the genetic makeup of a small population over time. Population genetics is a much bigger picture, and this is where we're looking at how populations change on the large scale over time. So for example, if I were studying beetles on a mountaintop, and I noticed in the first year that it was 80% green beetles and 20% brown beetles, and the next year I noticed that it was 60% green beetles and 40% brown beetles, by studying the different gene pools in 1 year and the next, I could see microevolution. I can see how that population changed in the short term. Okay. So now I want to introduce this thing called the Hardy-Weinberg genetic equilibrium. And basically, Hardy-Weinberg were these two scientists that came up with this idea that basically said, if there's no change in heritable traits in a population, that population is not evolving. In other words, if they have the same genetic makeup year after year after year, that there is no evolution in that population. So the Hardy-Weinberg equilibrium states that unless there's some outside force, unless there's some pressure, genotype and allele frequencies, or the genes in the gene pool, tend to remain exactly the same unless some outside force acts on it. And Hardy-Weinberg said that there are 5 different things that could act to change the genetic makeup of a population. And the first thing I want you to notice here is that natural selection, or evolution, look at my giant arrow, natural selection is only one of the things that can change the genetic makeup of a population. So we've been acting like evolution is the only thing that can change a population's makeup, but really, it's only one of several things that could change the genetic makeup of a population. So in this video, we're actually going to be looking at just the first 3 things here. These are things that can change the genetic makeup of a population. So the first one that we're going to look at here is small populations and this thing called genetic drift. Okay. So I want you to imagine a situation where I flipped a coin 10,000 times. So we know we should get heads approximately 500 and tails approximately 500. So if I got 700 heads and 300 tails, that would seem a little suspicious. That's way off what I expect. But if I only flip that same coin 10 times and I got 7 heads and 3 tails, that wouldn't seem all that suspicious because, I only did it 10 times. It's not very likely to get what I expect. And what I want you to take away from this is that the smaller the sample, the greater the chance of getting change or deviation from the expected result. So that kind of works for populations too. If I have a really small population, I'm much more likely to get changes in the gene pool just by chance. Not by natural selection, just by chance. Whereas if I have a very large population, it'd be very hard to change the genetic makeup just by chance. So let's look at a little bit what I mean here on the next slide. Okay. So I'm going to introduce this idea called genetic drift. And genetic drift is the idea that just by chance, and that's the big key here, just by chance, I'm changing the genetic makeup of a population. It has nothing to do with natural selection. And like we just saw, smaller populations are much more likely to be impacted by genetic drift because they're more likely to deviate from ideal results. So maybe I lose alleles, perhaps, and that could change the genetic makeup of my population. And we're going to look at 2 ways this could happen. There's one type of genetic drift called the bottleneck effect, and the other type is called the founder effect. Okay. So let's look at an example. So here I have a nice population of beetles, and if we look at this picture, there's 5 brown beetles and 3 green beetles, and they're, living their beetle life pretty happy. And then this guy comes by, and just by chance, he steps on the beetle population. He didn't mean to. He didn't even see the beetles, but he smushed them, and look at 2 of the green ones died, and none of the brown ones died. Now, it was not that the brown beetles were, better adapted. It's not that they had better adaptations that helped them survive. Just by chance, only green ones died. So therefore, I went from a population that was about half green, half blue, and now I'm mostly brown. So I've seen a change in my gene pool, but it has nothing to do with natural selection. Just by chance, I changed the genetic makeup. So in this case, the survivors were luckier. They were not fitter. They weren't better adapted. And this is genetic drift. Now, one thing I want you to think about, if this had been a humongous population of beetles, if I'd had 5,000 beetles and this guy smushed a couple, it wouldn't have been that big of a deal. I wouldn't have really changed the amount of brown versus green that I have in my gene pool. So as you can see, because this population is small, it's being more strongly affected by genetic drift. Okay, so now let's break down the 2 types of genetic drift. The first type is called the bottleneck effect. The first type is called the bottleneck effect, and this is basically when you largely change your gene pool or you lose genetic diversity because some catastrophic event happened to your population that by chance killed off a large percentage. So maybe if I had an earthquake come in and affect a forest, and a ton of the deer in the forest were killed. It's not that the ones that were weaker were killed or the ones that were more fit survived. It just by chance, a whole percentage of population was killed and left only a small amount behind. Now, it's likely that the ones that are remaining don't represent the same genetic makeup as your original population. So another example are elephant seals. So in the 1700s and 1800s, elephant seals were hunted to the point that their population was so small, less than 100, that they had nowhere near the original genetic diversity they did. The ones that survived just by chance were, not of the same genetic makeup as the original larger population. So I love this picture. This shows an excellent example of the bottleneck effect. You can see, so here's my original population of organisms, and they have some purple, some green, some red, some nice diversity, and then some catastrophic event happens, and most of them die, and only a couple are left. You can see my new population looks nothing like my original. So it's called the bottleneck effect because only a couple organisms make it through the neck of the bottle. Most of them don't get past the big catastrophe, and the remaining population has a wildly different makeup than the original. And it's not because, the purple ones here were more fit. It's just by chance, more purple ones survived. So the other type of genetic drift is called the founder effect. And this is basically where a small group of organisms go colonize a new habitat. And that small group that goes and colonizes the new habitat is very different than the original gene pool of the population that it came from. So it'd be kind of like if I had a colony of M&Ms. If M&Ms were an organism, and I stuck my hand into the bag and grabbed a few M&Ms, and then brought those M&Ms over to my desk and let them start their own M&M colony, the likelihood of me having every color of M&M represented in my new colony is not very high. So I've changed the makeup of that population just because a couple were separated out. So let's look at an example with. So here I have some beetles. I have this nice, varied beetle population with lots of genetic diversity. And then I take these 4 beetles and I bring them to a new island and let them start their own beetle colony. And then I take these 4 beetles and bring them to a different island and let them start their own beetle colony. Look, several years later at those 2 islands, the 2 new beetle colonies look completely different from one another because they were founded by different subsets of the original population. So you can see I'm changing the makeup of this population just by separating out a small section and allowing them to start a new population. And again, this has nothing to do with natural selection. It's just by chance that I'm changing the makeup of these populations. So that's the founder effect. That's the first thing that can affect the Hardy-Weinberg equilibrium, affect that state of no change. The second thing that can introduce change into a gene pool is migration. So maybe I have one population over here of beetles that's mostly brown, and one over here that's all green. If I get one brown beetle to migrate into this green population, well, now I've changed the makeup of this population. Now I have some brown where I didn't before. And again, it's not that the brown allele was favored by natural selection. I changed that population just by chance. So migration, or gene flow, is the fancy bio word for migration, tends to reduce the differences between populations because I'm getting mixing. And gene flow, we're just defining as the movement of fertile individuals and their genes between populations. And then finally, the last thing that we're going to talk about in this video that can alter the Hardy-Weinberg equilibrium are mutations. So again, if I introduce a mutation into a population, it's going to change the genetic makeup of that population. And that mutation might be helpful or it might be harmful. So it's not necessarily being selected for by natural selection at this point, but it is changing the makeup of the population. So for example, if I had a green beetle population, and then while this beetle had some eggs, in one of her eggs, there was a mutation, so one of her eggs had now the gene for brown. Now I have one beetle that's brown in the population, so I'm changing the makeup of my population here. And as we know, mutations are the ultimate source of all genetic variation. So the last thing I wanted to let you know is that mutations very rarely are helpful. So most of the time, they don't really affect the gene pool. It's only on rare occasions that they're actually a helpful mutation will they become very abundant in the population and become favorable. So occasionally, natural selection will act on them, but most of the time, they won't really have a big impact. So in the next video, we'll talk about the 4th and 5th thing that can affect the Hardy-Weinberg equilibrium.